In the prior segment, we started the range sum call and went over the code to set up range sum's stack frame, that code being the first few lines of the range sum code here. So let's finish the range sum call now. The loop here on lines 13 through 24 implements the for loop in the C code that adds values from low up to high and puts the total in sum. The body of that loop is actually at the top here. Lines 13 through 19. And it implements the C code sum equals sum plus low plus plus. So its job will be both to increment low and also to add low into sum. Lines 14 through 16, as the comments indicate, load low from the stack frame, and recall that that's at fp minus 8, and then increase it by 1, adding 1 to the value in R3 to put it in R2, and then write it back into that same stack frame location, and that in effect does a low plus plus operation. And so we get to our first in-lecture question. Consider now lines 17 through 19. These add low into sum, drawing it from, of course, offset minus 4 relative to FP. But do they add the value of low as it was before incrementation or after incrementation? Explain your answer. The answer here is that they add it as it was before incrementation because what they add is R3. Load R2 with sum, and then line 18 adds R3 into that, and ultimately it is R3 that gets copied back. R3, as you know from above, still has the pre-incrementation content of low. It was R2 that had the incremented value. This is an important question and answer because it illustrates the exact behavior of a C post-increment operator. The C expression low plus plus increases low by 1, but its value is the original low value, not the incremented value. The corresponding assembly retains the original value, like we did in R3, and uses it even though the variable has been increased. A pre-increment operator, plus plus low, works the other way. It increments low and has the incremented result as its value. So, question 2. Adjust the code on lines 17 through 19 so that instead it implements the expression sum equals sum plus 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 low, doing a pre-increment instead of a post. Well, to do that, all you have to do is swap R2 and R3 in every instance in those lines. So if I used I'll load the sum value into R3, and I'll use the R2 value that I still have from above, the incremented low, adding that to R3, and then we'll put R3 back into the location. So really all we need to do is use R3 instead of R2 in the operations to store sum. Like that. So I'll put those back now that you have a chance to look at it. And let's move on to the loop test. The loop test is actually on lines 21 through 23, and we'll explain why it's down there in a bit. This checks to see if low is less than high and jumps back to L3 for another iteration if so. So you can read the code readily enough. It's loading R2 with low and loading R3 with high and comparing the two and doing a BLT if R2 is less than R3 or if low is less than high, back up here. Okay, here's a question though. The C code did specify a while loop, so the test should be at the start of the loop, before the first iteration is even run. A test at the end of the loop seems like a do while. Is there a bug in the assembly? Think about it. And the answer is no, there's no bug, and it's because of line 12 here. Line 12 jumps down to the test, avoiding the loop body initially. And then it apparently would work properly after that because we do the test and then jump back up and do the loop body if the test is true, and so on. Okay, so apparently it works, but it's kind of odd. Why do it that way? Instead of just putting the loop tests up at the top,
and jumping around the body past the loop when the loop test is false, like we did in earlier examples. To have a hint here, compare the number of branches needed in prog4's loop here versus earlier while loops with the test on top. Well, the answer is that after the one-time jump to L2, each iteration of the loop requires only one branch. This one here back and back over and over again. And that reduces it from 2 branches to 1. So instead of a branch at the top that would go around the body and a branch at the bottom to go back up, we have only one branch, each iteration through the loop. Are branches such a big deal that we'd like to avoid them? Yes, as it turns out. And the reason has to do with the pipelined architecture of ARM processors. It's a topic we'll examine later. For now, though, get used to this odd test at the bottom while loop, because compilers like to translate while loops this way for efficiency to reduce the number of branches. All right, the last part of range sum is lines 26 through 29 here, and they implement the C code return sum. Specifically, what they do is remove range sum's stack frame and return back to line 47 in main, returning the value in sum in R0, and the calling convention expects R0 to contain the result of the function call. At least if the result is a simple one-word value like sum. There can be more complex cases. Okay, so line 26 loads sum into R0 to be returned. Now what I have to do is remove the stack frame. Line 27 changes SP to point to the old FP value, copies the current FP into it. So think about what that's going to do. We're dropping SP down to here now, kind of keep it off to the side, pointing the same place as FP. This effectively removes all the local state, high, low, and sum. Note that we do not deliberately erase that state by setting it to 0, for instance. We don't need to. Since it's no longer part of the runtime stack, it can just be left as garbage data in memory to be overwritten by some later stack frame. The main will expect its original FP to be unchanged upon return. So, line 28 uses SP as the address register, fetches from it the old FP to go back into FP, and while we're at it, remember that that comma pound for it is an after addition, while we're at it also moves SP down another word. So to be sure you understand, describe what diagram changes we should make to reflect the result of line 28. Okay, so the answer is that FP now points down to the bottom, or near the bottom, of the main stack frame, and SP now points to the return loc. All that now remains of the range sum stack frame is that stored LR value, which line 29 loads into the PC, moving SP another 4 bytes down to leave it at the top of the main stack frame, where we started. And again, a question, just to be sure we're all on the same page here, how do we branch back to line 47? There's no B instruction. And the answer is copying a value into the PC is a branch, since it changes the program counter and thus the next instruction to be performed. So we are in fact returning back to line 47 in the main. Now upon return to main, line 47 stores the result from R0 into FP offset by 4, which again is the location in main stack frame for variable total. So whatever our result will be, 145 I believe, given the values we passed, goes here. So looking briefly at the original C code, we've completed this line here in main, total equals range sum. The only remaining thing then is to do the printf, total equals %d or is %d, and pass the total.
So assembly lines 49 through 51, right in here, accomplish that. 49 sets up the first parameter. Per C rules, the parameter total is %d is a pointer, recall. We discussed that in earlier lecture. A pointer to the start of the total is %d string. I don't have the entire S file here, but I'll bring it up briefly to look at, and we'll see that that string is preloaded at label LC0, complete with the ASCII 0 value expected at the end of all strings, and the string's address is stored at L6. So here's that code with the string at LC0, just above main, and then down at the bottom we have at L6 a word that has the address LC0 in it. Sorry, I should have scrolled that up. A word that has the address LC0 in it. So, as a net result, LDR R0.L6 loads the string's address into R0 to provide the first parameter for the printf call. And a quick question, a review really of LDR STR concepts, replace line 49 with a different version that eliminates the need to explicitly declare the word at L6. And that, as you may recall from earlier lecture, can be done by saying equal.lc0 thus, and that would automatically create that L6 memory location containing the address represented by LC0 for us. Now the second parameter, total, is a lot easier. Line 50 simply loads it from the right offset in the stack frame into R1. And then finally, of course, line 51 makes the call to printf. Now that leaves us with lines 53 through 56 here, and they deserve a bit of explanation. Main returns a 0. I'll bring back the C code here, with apologies for having omitted that line earlier. It is properly in the C code to have a return 0 from main. But then, if that's so, what does it return to exactly? Who called main? The C compiler creates code that calls main and automatically starts the program at that code. That code gets the return value from main, and it uses it as the exit code for a SWI call, as we've seen in the handwritten code. That main caller is largely written in assembly and silently added by the compiler, so we don't have to look at it closely. But it does mean that main is called with a return location in LR, and thus is expected to adjust FP and SP and to retain the LR value, etc., just like any other function. And that's why those two words down here at the bottom of main's runtime stack have been standing there all this time. Lines 40 through 43 at the start of main set up a stack frame for main in the same way we did for range sum, but with just one word, 4 bytes, of local state for total. And then lines 53 through 56 put the return value 0 into R0, and then undo the main stack frame in the same way that we did for range sum. But where is the printf code for line 51 to branch to? Recall from earlier lecture that the Unix LD command takes incomplete code generated from AS and fills in missing libraries, like printf. The LD command would see the use of printf in the assembled prog4.s and link it into the final executable. But we don't even need to run the LD or the AS commands to assemble prog4.s. Any assembly program that has a main function can be assembled by GCC itself. Bringing up a Unix command line here. And the GCC is smart enough to recognize an assembly file as a command line argument and run both AS and LD automatically. Indeed, you actually have to do it that way because AS doesn't know to add that main caller we discussed earlier, but GCC does. So to assemble prog4.s, we'll actually use GCC, here are g4.s, and output to an executable prog4, which will be complete with a printf function. And then we run prog4 and get the 145 as expected.